Okay, we're at the top of the hour, and so I don't want to waste any time today, but I want to say hello and welcome to the first gear technology webinar of the year featuring Productive Robotics. They are going to be talking about how our cobots deburr their own gears, how we automated our worst shop job. The highlights today include open and enclosed cell solutions, scrap rate reduced from 10% to 1%, 2 times productivity increases with 100% consistency, and no robot experience or third-party integration required. We are also joined with Kevin Meister, who is the application specialist at Productive Robotics, who has helped over 100 companies automate processes ranging from welding to finishing and deburring, bridging the gap between robotics theory and what actually works in a factory environment. I will ask that if you have any questions, you please put them in the chat for now, and we will enter them during the live Q&A session at the end of the presentation, where you will also be able to raise your hand, and I'll call on you so that you can ask any questions you may have in the live environment. But without further ado, I'm going to hand it over to Troy and Kevin to go ahead and get started. Thank you.
Thanks, Rebecca.
I appreciate that, Rebecca. Thank you for the great introduction. So I'm Kevin. I'm the application specialist. As she mentioned, it's my job to help people figure out how to automate all kinds of different jobs at their facilities. I've been doing it for quite a while. I'm doing it for Productive Robotics. Productive Robotics is a collaborative robot manufacturer. We are based in Santa Barbara, California. That's where our offices are. It's where our factory is as well. One of the many things that differentiates Productive Robotics from some of the other robots that are on the market is the gearing system that we use in all of our joints. Our robot is a 7-axis or 7-joint robot. Each one of the joints has about 7 gears in it. So each one of our robots is 49 gears before it leaves our production floor. We brought Troy in so that he could help modernize what our gear manufacturing process is like. And once he got that down manually, we have the benefit of making robots. So he started turning his attention towards automating some of the jobs that they no longer wanted to do manually. So what I'll do is I'll go ahead and let Troy talk a little bit about some of the gears that we actually make. Troy, why don't you tell everybody what's special about our gears? What are they?
Well, hello, everybody. Thank you for joining us. I am Troy. And yes, as Kevin mentioned, I'm the gear geek here. Very proud of that. To answer Kevin's question, we cut basic spur gears for our robots. Each machine has a little over 49 gears inside of it when it's complete. Our gearbox is redundant. And generally, the gear cutting is pretty straightforward, but they're very accurate gears. We cut an AGMA 12 across the board as an average. Some of our motor pins even go up to 14s with our equipment and our tooling and our capability. So let's discuss where we were, huh?
Yeah, so you were making the gears. So we have our own gear manufacturing machines, of course, the shapers, the hobbers, we're cutting blanks on lathes. And then you were doing a manual deburr process. So why don't we start by talking about what that process was like?
Well, like most shops, I've spent thousands of hours behind the deburring wheel, unfortunately. That's just part of the gear making or machining world, is that you have to, at some point, deburr your parts. And especially with my machine shop that I owned, a lot of our business was aerospace when it came down to it, medical and aerospace. So the deburring was critical. Absolutely critical. We couldn't have a rejection when it came to the military. So, doing things by hand, well, you made it work, but you had a lot of difficulties, inconsistency, and people just don't like to deburr. None of us did. None of us do. It's just this necessary evil, but it was really a perfect task that, again, nobody likes to do in any machine shop. And it's a perfect task to actually try to automate. I had those thoughts when I started.
There was another side of it too, right? Because eventually we got to the point where we were selling enough robots that we hit that production bottleneck.
Absolutely.
We're manufacturing gears fast enough, but we're not deburring them and finishing them fast enough. So we had to figure out a way to decrease the labor costs and increase the throughput. So why don't you go ahead and tell us a little bit about what the automation process was like once you decided you wanted to switch from doing it manually to doing it with the robot. What did you do? What was your experience like? How long did it take for you to get it down? And did you have to develop anything specific in order to make it work?
Well, we've actually developed what we've got over about a 4-year span where we kept tweaking, refining, building some new tooling. Just like any machine tool, I consider our arm really another machine tool. A lot of the secret is in the gripper tooling, the part holding, like any machine tool. The compound, the media that we were running the parts, our material against, our material is about 28 Rockwell. It's a nitroalloy material, so it Deburr is kind of tough. You know, it's like a hard stainless when it comes down to it. So we had to find the right media, the right compound to make that work, which we found, and it's about a 320 grit Scotch-Brite embedded nylon, which is available through different manufacturers. We spec that for customers now. We had to figure out where to mount the arm, what size of table to use, how we were going to hold the parts, how we're going to tool it. And we wanted to keep that very simple and easy for our operators, you know, which, you know, and I got to say that our young talent really has helped with that, as far as just kind of placing things in the right spot, making it user friendly, making it a maintenance less of a nightmare in a lot of ways. And so we have come up with a solution on that. And that's, of course, we're going to demonstrate today. What you're going to see is our prototype table that we actually are running. It's actively running right now as we're making this. Polishing our hardened post polishing of our hardened gears, which works extremely well. So we're going to address that a little bit too further in the video.
So what we're going to do now is we're going to show you guys a video showing a gear deburr process. It's going to be from beginning to end. It's going to show you the full cycle of one gear being deburred. We do have an overhead view that's stationary with a couple of switches in the camera view, so you can really get detailed shots. But the idea of this is for you to see how we use the robot to emulate all the movements we were previously doing by hand to present the parts to the wheel. Troy's going to go ahead and narrate it a little bit while it goes as well. Go ahead and hit play on the video so people can watch.
Yeah, so I thought it was important for the group to watch a full cycle in real time. And this is one of our smaller, what I consider our medium-sized little pinion cluster gear. And most we're going to step you through here in a minute exactly what you're watching. But you're seeing it deburring one half of the gear, ODs, the flanks, the ends of the teeth, which it's doing now. And then it's going to move over to the other wheel in a minute, less than a second actually, and deburr the other side of the gear, which we have the 2 wheels for. That was part of the development, is to figure out where the wheel should be and how we're actually going to put pressure against whatever wheel for the result. So now we're hitting the other side of the gear effectively. And you have to keep in mind, this is aerospace quality. We end up with a 2/1000 radius on all the tooth tips, on the flank tips, on the ends of the teeth. The result is amazing. So we're almost done with the cycle now. It's going to finish off the end, including the bearing journal. It's going to deburr the end of the bearing journal for us. And you can see the radiuses that we end up, about a 3/1000 radius on the ends of the teeth here. And we're killing 3 birds with 1 stone here, which is nice. Now we're going to go back and complete the cycle back into our part tray. And these are our standard part trays. We like using our standard trays. Most shops have trays, and we recommend to try to use their trays.
So the idea is that they can take whatever fixtures they're using to hold their parts currently in the shop, and then they can adapt them to fit onto the table so that they can have a recurring location they can pick those parts up from without having to redesign how they hold the parts in the shop.
Absolutely. Absolutely. And we've done some of that. You know, it depends on the configuration, how many parts you want to put on a table or on a machine tool, the same thing. But generally what we've done is we've stayed with our standard part trays so that we can flow them through the shop easily. And that seems to work for probably a lot of shops that have their standard part trays.
Okay. And now we're going to show a couple of the close-up stationary slides with explanations on what's going on in them, right?
Yes. Yeah.
All right. So right here, just to dive into it, this is just an overhead view of the whole setup. So you can see we've got the deburring platform. which has, of course, the wheel on top of it. We've got the fixtures on the table and the robot are all part of the package.
Yeah, and we had to kind of figure out the best place to to actually place these fixtures, and this is one of the reasons why we had the size of the table that we have, which is for our XL or extra large machine table. And we wanted to keep it simple, that you have the luxury of putting these part trays in a number of areas on the table. We are showing 2 trays right now. One's for another type of part number, which we switch back and forth very easily now, and the programming is already done for most of our parts, if not all of them. And so we're picking up out of our part tray, and then we're going to move over to what I consider our wheel 1, which is our left-hand wheel from the front. And this is important. This side of the wheel and the side of the gear is what we're doing on this particular wheel. We're pushing against our compliant base, which we're going to get into. We actually have a pneumatic slide that we're going to discuss that was very much a key secret for how we're actually deburring these parts. It gives us compliance against the teeth, but we are actually deburring the one side of the flanks on this wheel. So we start with the gear, and then we move over, next slide please, to the pinion, and we rotate the wrist to do this particular action, which you watched in the video. Okay, next slide please. And then we're deburring the end of the gear with rotation being down of the wheel. Next slide, we're going to move over to the wheel number 2, which is on the right side of the machine. And we do this because we want to hit the other side of the adhesive flanks of the gear. And then next slide, OD of the flanks of the pinion. And again, we're getting about a 2,000ths radius, very consistent radius, which is pretty much aerospace spec on this size of a tooth. This is a 0.3 module and a 0.4 module 20-degree spur gear that you're seeing. Okay, next slide, please. And now we're actually hitting the 3 different diameters. We're deburring the faces of the gear, and then we're also touching the bearing journal and deburring the slight burr that would be from the lathe. Works very, very well. So you see a before and after here. You see clearly we have very sharp edges, and then after we have it's about 2 to 3 thousandths. So let's say 2.5 average on the ends of the teeth. We shoot for 2. Yep. Okay, next slide. And then we place it back into the part tray. This is great. This is not confusing that way. We see there's a hole. We're putting it back. We're grabbing the next part. Once it's done, we can either pick the whole tray up, put the next tray on, or just have the operator shuffle new parts in as it goes. We typically shuffle more parts in as it runs. And so the operator walks over every half hour, whatever, sees where we're at. Once the tray is done, of course, the system stops, and he reloads or just replaces the tray. And that's kind of what we're showing here. I want to introduce that.
Okay, so now we're going to show you guys a little bit about the actual deburring platform. So this is a pneumatically controlled platform. What we found when we first started doing the deburring process, where we were just taking the part straight to the wheel on a table, is eventually the wires on the wheel were wearing down and the part was no longer hitting the wires and getting the same deburr. So in order to get improved consistency and uniformity across the board, we developed our deburring platform. Basically, the gist of it is that it uses air pressure to make sure that the part's constantly hitting with the same amount of force. Go ahead and show the video of this. So you can see the platform that it's mounted on. You can see how it slides back and forth based on the contact and the pressure from the part.
Correct.
It is, of course, adjustable. We'll show you some of the knobs on it. So you can see there's an offset adjustment as well as a pressure adjustment. So you can dial the pressure up or down if you want more or less movement out of the platform. And then you can have an offset that you can go and just turn the offset wheel.
So that is the offset right there.
Yes.
Is the chart. And then this is the pressure adjustment, which puts the pressure, the necessary pressure with the offset against the wheel. So the combined dial it's very adjustable and adds beautiful compliance. And of course, as we know with any machine tool, offsets are very important.
Okay, so now we're going to show you guys most of what you've seen has been on an open table format. We do also have an enclosed cell as well, so we'll go ahead and show you guys a little bit about that one. Go ahead. So the big difference on this one is that it's enclosed. It has doors on all 4 sides, so humans can access and move in trays, move out parts, and you could run jobs from the outside. One thing that's interesting about this is we do the deburring before our parts go out to get heat treated. And then when they come back from being heat treated, we do finishing with the same process. So this is actually finishing, not deburring.
I consider this is our finished polishing, yes. Yeah, and you can see the compliance. See, this is the same setup, the same wheels, same part in this completed cell. Okay.
So now we're going to talk a little bit about some of the results when we switched from doing our deburring manually to doing our deburring automatically. Troy can speak more to that than I can because he's the one who actually does it. So why don't you go ahead?
Well, as you see on the screen, you know, we increased the throughput. I would say this is conservative. We've probably gone maybe three fold from what we were doing by hand. It doesn't necessarily mean that the speed has increased a lot, but the consistency as far as the loading, the machine running, just like a CNC tool, if you keep the spindle turning, just like once we're doing the gears, you keep it loaded, you keep the machine running, the throughput is incredible. And your operator is very happy because he's not standing in front of the wheel.
Okay, well, and the other side of that too is now that your operator is not standing in front of the deburring wheel holding parts to it, they're free to do other things.
Absolutely.
So not only did it increase the throughput of the deburring process itself, but it also freed up our employees to do other tasks, which increased our productivity in other areas.
Right. And you see, we have it, you know, we came up with about 10% scrap rate, mainly because people were dropping the parts by hand. I mean, that was our scrap, is that it would fly out of your hand, fly out of the tooling, onto the ground, on the concrete, onto the table, whatever. And with our parts, they're just scrap as soon as they touch the table. So we went from roughly 10% with us all being as careful as possible down to a 1% or even less by doing it with what we've got now with the robot.
Okay, and obviously consistency. Once the robot is taught how to do a job, it will repeat that job exactly the same way every time.
Absolutely.
So once you dial in the deburring process from beginning to end on your part, you're going to get that same consistency across the board.
Yeah, and I've got my guys trained, you know, just like any machine tool, is that, you know, they're watching the part, we're inspecting, you know, we run a whole tray, maybe let's say 30, 40, 50 parts, depends on the tray and the size of the part. They'll take a look at the last part. We might want to dial the offset, let's load it again and keep running. So we have 100%. We have very consistent quality at this point. Yes.
Cool.
Yeah.
Okay, so now what I'm going to do is, again, one of the things you may have heard us mention a couple of times is that our system is a no programming system. So I'm actually going to show you how the teaching function of our robot works and what the process is like in order to bring a part to the wheel and teach the robot how to do it. So if you can bear with me while I walk on screen. Okay, so ignore the lathe I have behind me. Typically when we do this demo, we're showing that you can unload a part from a CNC machine and bring it to a deburring wheel in process. But for now, I'm just going to show you how to pick up a part. I've got a little brick here and how to present it to the wheel and do a couple of quick passes. So I'm doing this all using controls that are built into the handle here. So I've got buttons on the handle that I can use to control the robot's movements. I've also got buttons to open and close the grippers. And I've got another button that does what's called setting a waypoint, which is just setting a point you want the robot to travel to while it's on its path. So once I get in teaching mode here, now I'm going to teach the robot how to pick up this part and bring it to the wheel. So I'm going to start by setting a waypoint up here to make sure that the robot is not going to crash into anything as it goes to grab the part. I'm going to bring the robot down to where the part is. I'm going to push the button to close the gripper. Then I'm going to set another approach point over here. And I'm going to come down here and set another move. Now for this one, I'm going to do a linear movement. So the robot will travel in a straight line. So I set one move on one side of the wheel, the next move on the other side. And then I'll just rotate and come back as well. Then from there, I'm going to hit one more waypoint up here to make sure the robot again doesn't crash into anything and bring the part back down to where it originally was. Now, the robot can go ahead and run that job. And assuming, of course, that I put everything back where it's supposed to go, which I did, that's good. So now the robot's going to hit all the waypoints I set. It's going to pass through the wheel, but of course it crashed into the wheel. So let's just go ahead and adjust that waypoint real quick to make it work. Is it this one? It is. So we're going to pull you out a little bit. And then go over here. Okay, let's try that again. And we'll just let it resume. All right, you know what? Let's start from scratch because obviously I messed something up there. So I'm going to go learn new job. Now, waypoint, grab the part. I think the problem is I got too distracted doing my discussion. Set a waypoint here on a linear path.
The screen just popping up.
Pop up and put the part down. Okay. So as you can see, it's pretty quick and easy to make adjustments to jobs too. And there we go. That's all there is to it. Go ahead and switch the camera view.
Okay. Back to mill.
Okay, so that's a demonstration of how the teaching function works and also how to make adjustments when you make a mistake on the teaching. Where are we going from here?
I'm glad you're.
All right, now we're going to do a tour of our deburring room and our gear making room so you can see some of the different equipment we work with and some of the gears we make. Go ahead.
Let's take a quick break. I really want to show you something. This is our OB7 mounted to our 132 micron. Not only are we deburring our gears, we're also loading and unloading the micron now successfully. And we're running production. We've run thousands of parts for this machine now. So let me start the robot. We're using our standard part trays. We're regripping because of the tray, which is what that fixture's for. Puts it in configuration for loading. Pneumatic cylinder against the tailstock. Closes the door. And our I/O turns on the circuit to turn on the cycle of the machine. And now we're unloading. That's our blow-off kit. And places it back in the tray. Okay, well, it unloaded. It blew off the dead center with our blow-off kit, and then it unloaded the part into the other side of our part tray. Very clean, very clean. Let me show you something else. This is our A33 micron. These are medium-sized part clusters. We're regripping like we did on the 132. We like to use our part trays. 4 different part numbers of similar configuration. This is our medium-sized cluster gears. Now it's going to load it into the spindle. Come back. Push the cycle start. And the arm comes back. All right, that's the A33 micron that we retrofitted. There's many machines in your shop that you can retrofit successfully with an OB7 Cobot.
I still think it's really cool, the stuff you guys are doing back there.
Yeah.
And so I believe now it's time for the Q&A, if I'm not mistaken.
That is correct. Thank you so much, Troy and Kevin. Troy, I don't know how you were in 2 places at once just then, but I enjoyed watching you demonstrate both areas. Fantastic. We've got a lot of great questions in the chat, so I'm going to go ahead and start with those. If anyone wants to ask something just using your voice, you can raise your hand and I'll call on you, but I'll go through these first. Can you please elaborate more on how there is no programming on the parts tray?
Yes. So our robot uses what's called a grid function. So the way the grid function works is you can see in those part trays, all the parts are on a uniform grid. So with the robot, you teach the 4 pickup locations for the 4 corners. So it'd be similar to the way I taught the pickup location over there, but with 4 locations instead of 1. And then you just tell the robot how many rows and how many columns of parts. It'll figure the individual locations for each individual part on its own.
What are high-low mix or mix low volume gear shop? We are a high mix low volume gear shop. What sort of quantities does make the most practical sense?
So it's going to be variable from shop to shop, and it's also going to depend a lot on how long the deburring process is on your specific part. In general, most shops that use our robots will use them for runs of 5 parts or more. The justification behind it is usually if it's going to take me an hour to do it by hand, I'll have the robot do that and I'll spend my hour doing something else. So we can work with you if you give us some information about your specific parts and how long your manual deburring process is like and what it entails. We can give you a better idea of how long it would take to deburr using the robot and what kind of throughput you'd get.
Yeah, and on that note, we started running about 100 parts at a time when we started doing the development on the deburring, and also when we started loading our older machines with Cobot. So our volume has gone up easily now that we are automated.
Is the technology exclusive for your robot?
So,
meaning, can another company's Cobot be used for this application?
In theory, yes. You would need to get similar support equipment like the deburring platform that we offer. Our deburring platform is designed to work with our robot. You'd have to look in to see if there are other options available, which I don't know about all the competitors that are out there. But in theory, yes.
Yeah, really, a gear shop has developed a system, including the platform, to do this successfully for a gear shop. So you're getting a gear shop development with our system, and that's kind of the beauty of that, is it's a complete package. Somebody doesn't have to piece things together and be kind of, maybe not great that way. Our system's integrated.
Fantastic. Have you evaluated this system with other types of abrasive wheels? Someone is interested in the PG2 gripper's ability to securely hold the part while using a rigid wheel compared to the brush configurations shown.
Yes, go ahead.
So we have experimented with different types of wheels. It is definitely possible. Sometimes you have to grip the parts in specific ways to make sure that they don't get kicked out of the gripper. One of the cool things about this gripper is that it does have removable fingers. So you can custom make fingers that'll do it in encompassing or and around the grip that are designed to fit specifically on your part. And you can even see some of that in the videos. We have custom fingers to hold our parts. So that way you can prevent the part from kicking out on a more abrasive or friction-based wheel setup. And you can also use other grippers with the robot too. So that's also an option as well.
Can the robot detect if a wheel is worn or there isn't enough contact with the part?
The robot can detect if it's not getting the right amount of pressure, and it can error out. Similar to how it did when I was doing the teaching of the job, and it crashed into the wheel and the robot just stopped and started blinking red. That was a force error. It can also do that if it doesn't feel force that it's supposed to.
It's all settable, all programmable.
But you don't really have to worry about that when you use the deburring platform, because then it's designed to make sure you're getting the even amount of pressure against the wheel every time anyways.
Yeah. That's really the beauty of the platform.
Yes.
It's just that.
What is the upper limit on the radii you can repeatedly produce? And can the system generate different sizes of, maybe I'm not saying that word right, RADII. What is the upper limit on the radii you can repeatedly produce? I guess basically the sizes.
I think he's talking about
on
the
a single
radius
part.
you get on the.
As far as the part size, is that the question?
Yeah, you're limited more based on weight than you are on the circumference or the size of the part. I've got 5 different models of robot. The weakest is 4 kilogram payload. The strongest is a 16 kilogram payload. So we're just under 9 pounds up to about 35 pounds. Any part that the robot can pick up, we can bring to the wheel and hit it. So you're more limited on weight than you are on size.
Yeah. Okay, he did specify that it was the size of the radius on gear 2. So.
All right.
Yeah, we have a pretty recent application where a shop is actually using one of our larger XL machines and picking up big, large steel saw blanks and then deburring them off the saw. And we're talking getting up to 10, 15 pounds. So we can do quite a bit with our bigger machines.
Why is that specific table necessary versus just having the robot move the part on the wheel?
So the wheel wears out over time. And what we found is that is a nightmare for consistency. And if you're trying to get even consistency across all your parts, you want to make sure that the wheel is always getting hit with pressure on the part. So the platform compensates for the wear of the wheel over time. When we originally started doing our deburring, we were not using a platform because we had not developed it yet. And that was the issue that we kept facing, was that we were not getting consistent throughput on our deburring. And so when we developed the platform, we did that to make sure that everything was completely automated and consistent across the board.
Okay. Do you offer a solution for internal ring gears under 2-inch pitch diameter? Very specific. So the person may want to touch base with you, but go ahead and yeah, if you want to take that, Troy.
Yeah, we actually have an application, a customer that actually bought that completed cell you saw, and they're deburring, I would say, fairly fine pitch, maybe about a 32 pitch, something like that, internal gear. It's an aerospace part, and really all it required was a smaller wheel adapted to the end of the motor, which we helped them with, and voila, we had them running in less than a day. And I think that job is still running. I think that's been a couple months they've been running it. So yes, very, very, very simple and successful for internal gears also.
Next question is, this attendee produces universal joints that would require more than just spinning the part against the wheel. It would have to swing around ears and other shapes. How would that be programmed?
So it would be set with the different motions. So as you're setting waypoints, you would have one waypoint here, and then you would have the robot travel across the path setting waypoints that you wanted it to follow. So you'd be able to get all kinds of different angles, hitting against the wheel, rotating into the wheel, rotating out of the wheel, gripping from the side, top, bottom. You could see in the video where we showed the robot coming at multiple different angles to present the part to the wheel. Again, every part's a little bit different and unique, so I can't speak universally for every part and say, yes, absolutely. But if you show me some of the stuff that you're trying to emulate, video of what you're doing manually, then I can tell you, yes, our robot can emulate that, or no, it can't. One of the big benefits about our robot having 7 joints or 7 axis is that I can reach in ways that other robots can't because I have an extra joint. So sometimes I can reach around obstacles to pick objects that are up behind them, or reach around the side of the wheel to present the part in a way that you might not be able to do with another robot. So the versatility of the movement of the arm really helps with those changing angles and movements across the wheel, not just holding it in place and rotating.
Thank you. A common question that is coming up now is pricing on investment. So we are just curious. I think a lot of people are, and obviously this is going to change probably depending on what people are looking at. But for what you showed us today, is there a price that you could share?
Yes. So the open cell table with one of the two smaller sized robots is going to be about 46,900 for the whole setup. If you want the enclosed cell, it's going to be about 1,000 more. There's some variation based on different accessories and things you'd want based on the weight of the parts and the size of the robots, but those are starting points.
Fantastic. The dust and particles that are falling from the wheel are falling on the table. How do you prevent this using an automatic and unmanned process?
So there's not going to be a way to do it fully unmanned. At a minimum, people are going to have to be bringing parts to and from the robot. The robot's a completely no maintenance robot, but you do want to make sure that you keep it clean. So as it gets dirty, you're going to want to wipe it down. Typically, what do you guys do for your cleaning?
Yeah, well, you saw in our demonstration that we have an open table. You don't see we have some ventilation above it that we kind of deal with the dust particles. And with these wheels and our material, we don't have a lot of dust. It depends on, of course, the material and the compound, the media you're using for the different dust particles. But we are actually, it's one of the things that we're discussing is a filtration box that'll be available. Some of our customers already have them, and so they just adapt their suction of that filtration system to the table, to the area. You just have to kind of get it close. And again, it's really a customer specific issue as far as how much dust and what material and all that. But yes, it's very addressable.
So you're using a combination of exhaust and then just cleaning the workstation at the end of the day?
Correct. Yes.
Yeah. Thank you. So how easy would set up for the Deburr process for helical gears? And I think with that same question, I'm going to add on one that we had talked about previously, which is different machines that you have that are not in use in your facilities now. What does that implementation look like? And does it require integrator or coding for that? So I guess one on the helical gear setup, and then just overall using and retrofitting implementations on your current machine.
Oh, awesome. Well, on the helical gear side, it's really the same as a spur gear as far as implementing the rough programming, how you address the wheel, what side. It's going to be very, very similar, if not almost identical. You have a helical lead angle to worry about, but the beauty of our robot, that's very programmable. To follow the lead, if that's what you're working, if it's a very large, long face helical gear, very doable, very adjustable. It's a beauty of our system that way. And you can finish the other part of the question.
Okay, so our system out of the box to assemble takes about an hour to 2 hours, depending on how good you are with a wrench. Once you have it set up, most shops are up and running with the first job within an hour or two, depending on the complexity of the job. So it's going to basically depend on how comfortable you are working with new technology and how familiar you are with the manual deburr process. You're going to want somebody who knows all of the angles that they need to hit and how long they need to rotate and all those things to teach the job. Once you get the rough draft of the job taught, which is the bulk of it, then it's just refinement. And going in and making a quick adjustment to something doesn't take much time at all. Once you get it refined, then it'll repeat that process perfectly forever, assuming you're loading the same amount of parts in the same fixture and you're putting it in the same location on the table. That job's stored in memory forever, so you can run it repeatedly.
What is the precision and repeatability of positioning?
Well,
0.04, I think.
Yeah, I mean, for what we're doing, it's very, very accurate. I mean, the repeatability of the machine is very accurate. It's in the thousandths of an inch, if I recall, as far as repeatability.
I think it's 0.04
But
mil.
for our deburring, it's not that critical. I mean, if you're getting within 20 thousandths on, you're doing pretty good. But our repeatability, I don't know. I don't have the number. You don't have the number, but it's very
I think it's plus or minus 0.04 mil.
Yeah.
Okay. No, I was going to say, how long is the delivery on the OB7?
Some of them I have in stock right now, and I could ship within 1 or 2 days. If I don't have it in stock currently, then it's about a 1 week lead time for us to put it together.
And there's a lead time for our cell.
Oh
We'll
yeah,
have to
the
discuss that.
enclosed cell does have
Yeah.
a lead time. That's 4 to 6 weeks.
4 to
But
6
the open
weeks.
cell, I can tell you, ship it out tomorrow.
Can this same deburring setup be used to load and unload machines as well?
Yes. So all of our robots all work the same way with the no programming feature, as evidenced by the fact that I've got a CNC machine behind me with the robot right here. And then you saw that I had a lathe in front of the Deburr setup. Yeah, we absolutely loading and unloading parts into a CNC machine was one of the very first things we ever started doing with our robots. And we are very good at it. We have specific packages for that too, that I won't get into, but if that's something that you're interested in, absolutely reach out to us. It's less expensive than the deburring platform.
We had a couple questions come in that have to do with the speed at which it operates. So one of them is, does it slow down when people come towards and are working near the machine? Is that something that happens automatically? And then does the enclosed system run faster due to the enclosure? Is it still running at the same speed as the one without an enclosure?
Good questions. All our robots are collaborative robots. That means in general, they move at collaborative speed, which is an industry standard. It's 10 inches per second. So all of the videos and all the features and all the demonstrations, we're moving at 10 inches per second. If you want the robot to move faster than that, yes, we can absolutely set that up. You'll need to have something called like a laser scanner or a LiDAR scanner. I've actually got one on the table right here, but you can't really see it. So I'll pull it up. Something like this LiDAR scanner that would mount under the table or above the table so that if somebody did walk up to the table, it would slow back down to that collaborative speed. The enclosed table would be able to operate at faster than collaborative speed without having to worry so much about the LiDAR scanner, except for when people open and close the doors, you'd want it set up for that.
Okay. You mentioned a little bit about it keeping track of the waypoints that you've set up in its memory. How much memory does the unit actually hold?
You're never going to run out of memory. You could spend, there's a limitation to the memory, but it's in the tens of millions. So even if you spend the rest of eternity teaching the robot how to do new jobs, it's not going to run out.
Yeah, some experimentation, and it's kind of fun. You know, my guys really enjoy it. They really enjoy running the robot to do that. It's fun.
Usually on your first part deburr, you're going to hit somewhere between 50 and 80% of the deburring process automated right off the bat. Some parts, like our gears, you will absolutely be able to get to 100% automated deburring, no human intervention. Some parts you'll need to have human come in and do bits and pieces here and there. Every part's a little bit different, and we kind of have to play with it. But at the end of the day, even something like we have different gears that are the same shape but different sizes. So once we teach the robot how to deburr one size, we'll use that job as a template for the other sizes. And if we need to add additional passes or slow down rotations, we can make those changes without having to start from scratch on every part.
Can you show us a bit about the programming interface?
I think I can.
Yeah, cable's right there.
Fantastic.
I still have all my camera views, right? Tech team? Yes. Cool. So you're on me, and then I could switch. Okay. So I'm going to switch back and forth between a couple of different camera views so you can see me, and then you can see the tablet I have right here and what I'm doing on it. So if I hit learn and then learn new job, for example, now the robot's in learning mode. It's ready to be taught. So now what I'm going to do is I'm going to use these controls that are built into the handle. So you can see I've got these buttons here. That's where I take control of the handle. I've got open gripper, close gripper, waypoint right here. So now using the buttons here, I'm going to come down and I'm going to set up my pick for my first location. Now you can see I've got two parts on the table now. I don't know if you can see these shiny bricks. They kind of match the table. But I'm going to set my pick point for the first part. And then if I switch to my tablet, you can see my pickup pattern is set as a single position. If I pop into here, now I can set it as a line. And I can say that the spot I'm in right now, that's my starting position. But then I have to tell it where the ending position is going to be too. So now what I'm going to do is move the robot to where the second part was. And that's going to be my ending position of the line. So now going back to the tablet, set the end position there. So now I've got my pickup set on a line. So after it picks up that first part, it's going to pick up that second part. But then I just pop up, I'll hit a waypoint over here, and then I'm just going to place it down over here to make the job nice and short. Now you can see on my tablet, I didn't have to go into the tablet and push a bunch of stuff, but I've got move, pick up, move, place, move, all set here. So from this learning mode, I can switch to working mode. And then when I hit go, once again, assuming I put the parts in the right location, yay. Now the robot's going to pick up the parts from where I told it to and put them down. It's going to hit every waypoint that I set and then go through the process and hit the second pick location and do the same thing and put the part down. Now, if I had this part still here, I would crash into it, and then this is where my error out. So I can see that my force safety limit has been exceeded. When that happens, human intervention is required. So if I move the obstruction out of the way and I hit resume, now the robot finishes up the job that it was trying to do. So hopefully that's a little bit more of the no programming function for you guys, show off a little bit better.
Thank you so much, Kevin and Troy and Productive Robotics for hosting this amazing webinar. I think we've had a really great group of people attend, and also these questions were pretty fantastic. I do want to reiterate that you will be receiving a full recording of this webinar that's going to come directly from Productive Robotics, along with some information to help you and your team understand more of the technology. If there are any questions, we do encourage you to go ahead and scan the QR code on the screen right now, or you can email or call and talk with Troy, who will be there and available to answer you and your team's questions or set up private consultation. But then again, thank you so much for everyone who joined us today. We really appreciate your support and for Productive Robotics and this incredible innovation. Thank you all.
Thank you, everybody.
Thank you.
Thank you, Rebecca. I really appreciate the opportunity to share this with you guys.